this time I want to cover the 3 equilibrium equations, and that's one of the first things we learn about in our first semester in our structural engineering bachelor's. First thing we need to know about them, so we use them to calculate reaction and internal forces like bending moments, shear forces, and so on. But we can only use them for statically determinate structures and systems. I'll leave a link to an article where I explain the difference between statically determinate and indeterminate structures. The 3 equilibrium equations, they consist of horizontal equilibrium, vertical equilibrium, and moment equilibrium. And what that means is basically for horizontal equilibrium that the sum of all horizontal forces equals 0. Right. I'll show an example later on. Then the vertical equilibrium is the sum of all vertical forces. And the moment equilibrium, the sum of all moments is 0. And yeah, let's try and see what that means for an example. So we have a very simple structure here, like a simply supported beam supported by a roller and a pin support and exposed to a line load of 2 kilonewton per meter, and the span is 4 meters. How do we use these equilibrium equations now? So the first step is step 1, to calculate the reaction forces. So they are here. We have a vertical reaction force and a vertical reaction force here. We call this a V and BV, V for vertical. And then the pin support also has a horizontal reaction force, which is a H. Okay, so in step 1 we calculate the reaction forces. Let's do that. We first say, okay, vertical equilibrium, so the sum of all vertical forces is 0. How does that look like? So we have our 2 supports, a V plus a B, and they are in the same direction, so that's why we add them. But then the line load is in the opposite direction, that's why we subtract that. So we have 2 kilonewton per meter times 4 meters equals 0. But now we have 2 unknowns, AV and AB, so we cannot solve this equation. So that's why we need another equation. But let's first do the horizontal equilibrium, which is sum of all horizontal forces equals 0. And here we only have AH as a horizontal force or load. So that's 0, and therefore AH equals 0. Now we have one more equation, and that is the moment equilibrium. And we have to choose like a location for that. Let's say we do it in point B. So moment equilibrium in B equals 0. So what do we have? We have AV, and we say this is the positive direction. So we have AV times 4 meters. We don't have an ABV because it's in the point where we do moment equilibrium. And then we have our line load, which equals, we subtract that, so 2 kilonewton per meter times 4 meters. but then only half the distance times 4 meters divided by 2 equals 0. And now we can see we only have one unknown, and that is AV. So we can solve that actually for AV. So we say, okay, we divide that, we say we divide that by 4 meters. So then we have AV minus 2 kilonewton per meter times 4 meter divided by 2 equals 0. Now we say plus 2 kilonewton meter times 4 meter divided by 2, and we can solve AV, and that equals 2 kilonewton per meter times 4 meters. That is 8, so then we have 4 kilonewton for AV. And now we can also solve BV because we have AV. So this equation here is AV. Sorry, we know that. So 4 kilonewton plus BV minus 2 kilonewton per meter times 4 meter equals 0. Now let's do this down here. We solve it for BV, then we have BV equals minus 4 kilonewton plus 8 kilonewton, because this one here is 8 kilonewton. Yes, and that is BV equals 4 kilonewton. Great, so we have BV, we have AV, and we have AH. So we calculated all reaction forces. Now in step 2, we can calculate, okay, this is really messy, I'm sorry for that, but it's the first time we try this format. In step 2, we can calculate internal forces. Right. Such as bending moments, shear forces, axial forces, and again with the equilibrium equations. Let's do it for this beam. We say internal forces. We have our beam. We do a cut here at 2 meters. We have our reaction force AV, and then our moment, our shear force, so moment, shear force, and then usually we have a normal force, but that's 0, so we leave it out for now. And basically we can do exactly the same again. And one thing I forgot is we also have to add our line load. Again, we can do vertical, horizontal equilibrium. In this case, we have AV minus V minus 2 kilonewton per meter times 2 meters, because we cut at 2 meters. And then we can solve the shear force. This equals 0, so we solve it for V. And then we have AV equals 4 kilonewton minus 2 kilonewton per meter times 2 meters, also 4 kilonewton. So AV is at this location 0. And then moment equilibrium equals AV times 2 meter minus 2 kilonewton per meter times 2 meter times half the distance, which is 2 meter divided by 2. and then minus moment equals 0. Now let's solve that for the moment. AV is 4 kilonewton times 2 meter is 8 kilonewton meter minus 2 kilonewton per meter times 2 meter times 2 times 1 meter equals 4 kilonewton meter. 2 times 2 is 4, yes, equals 0. Sorry, not equal, but this means that our moment is 4 kilonewton meter. Alright, so that was it. It was very messy, and let me know in the comments if you like this type of calculations here on the iPad. But I hope you maybe understood the 3 equilibrium equations a bit more.